Okay, so let's start with this one. Number one. If this reaction is first order, right, so we're actually told that this reaction is first order in hydrogen peroxide. So whatever its term will be, it'll be first order. Okay, we're given that. Second order in I. So the concentration of I, which is an ion, is second order. Right? So we're told that. And zero order in protons. Okay, so what does the rest of the rate law look like? Well, we start off with rate here, right? And then we have a constant. Right. So that would be the starting point for your rate law. So here's the thing. What is this term right here? That's 1. Anything to the 0 power is 1. So that one drops out. Right. That's the trick to this one. Okay. Just to see, I mean, we did one of those in class where we had a 0 order and it dropped out, but I thought, you know, that it went by so fast, maybe that one just flew over your heads. But I wanted to make this point. So that means the rate is K, H2O2 to the first power, I, negative I to the second power, and that's it. So E would be, gotta turn this thing on because E would be the correct answer. It would be tempting to do this one, right? But this is the correct, because that term drops out as 1. Okay. Let's scroll up and get the next one. All right. Number 2. Let's see, a reaction has this rate law. So if the rate equals K, and then A to what power? 2. And B to what power? 1. And C to what power? It's also 2. There's your rate law. What's the overall order of this reaction? Right. The order for, and with respect to A, is second order. First order for B, second order for C. What's the overall rate order for this reaction? You know what it is. Add them up. Right? 2 plus 2 plus 1 is 5. That's the rate order for the equation for that reaction. Let's see. Okay. Get that out of the way. 4. If the reaction, okay, 2 hydrogen iodide yields what? Hydrogen plus iodine. Which of the following will yield a linear plot? Can we tell? Oh, it says it's second order. Okay. Yeah, second order. Okay, we have one term. Remember, we typically describe reaction rates in terms of the reactants, not the products, because we're usually starting off at the very beginning when we don't have any products to interfere with the forward reaction. So in terms of this one right here, we have that rate, HI, to the second order. Now, this 2 and that 2 that's coincidence. They bear no relationship to one another because we haven't described a mechanism. All right, so this is experimentally determined. All right, so which plot will give us a linear for second order? Well, let's review. Right? 0 order. What's linear for zero order? Plot time versus concentration. That's whatever it is. It's the raw data, zero order. How about first order? Time versus what? Y'all remember? Natural log of concentration. Second order. This gives us the answer to the question. T versus what? The inverse of the concentration. So that makes this one right here. Inverse of HI versus time will give you a linear plot, assuming it's second order. Okay. I guess we're in agreement. I'll move on. Five. Which of the following statements about enzymes is incorrect? Okay. Read carefully the question. We're looking for the wrong one. Okay, so enzymes. They're usually proteins that catalyze specific biological reactions. Yes, that's true. They serve as biological catalysts, and they are usually proteins. Now, we didn't talk about the various types of enzymes. Most of them are proteins. Some of them are nucleic acids. Very few. They're equal to inorganic catalysts in efficiency. That actually, they're not equal to inorganic catalysts. They're extremely efficient, much more efficient than the inorganic catalysts. So that's our wrong one. Several thousand are now known. Yeah, probably more than that, actually, since this question was written. Molecules they react with are called substrates. Yeah, that's true. We didn't talk about that either. That's one of the reasons I put this question up here, so we could draw conclusions and get more information about enzymes as catalysts. We call the things that they act upon, the reactants, are called substrates. In case you ever encounter that in the future. But the wrong answer is this one. They are much more efficient than inorganic catalysts. They're very specific too, extremely specific for the particular reaction. Whereas inorganic catalysts, you can have, for instance, we can have platinum as an inorganic catalyst, and it will catalyze the decomposition of water in hydrogen and oxygen. It will also catalyze the hydrogenation of unsaturated oils. That's what the food industry does, or used to do a lot of. They take oils that have a certain melting point and smoke point, and then they hydrogenate them, and that would increase the temperature at which they could operate. The problem is when you hydrogenate a fatty acid, it produces a non-biological form, one that you don't get from nature. And that can create metabolic problems for people. But that's another topic. Let's see, I'm going to have to do this. Probably simpler to do it this way. I'm going to try to use this thing. It's okay for pointing, but at least on this screen, the scroll bar is out of reach. Number 8. Turn that into an 8. A free radical is a chemical species that possesses what? We talked about this. Oops. What is a free radical? It's any element or compound that possesses at least one unpaired electron. That unpaired electron makes it extremely reactive and dangerous for biological systems. That's why we have built into our metabolism, we have free radical scavengers, and we get them from our diet too. That's why they say you need lots of unsaturated fatty acids in your diet, like omega-2s. That's these 369s, omegas, 369s, any one of those will be good free radical scavengers because they have unsaturated, they have double bonds with these pi electrons floating around on the outside, and they can pick up those free radicals and neutralize them. Okay, so to answer the question, it has an unpaired electron right here. And your free radicals they can be neutral or they can be ions, either one, as long as they have that unpaired electron. One, sometimes they have more. 9, rate expression. What does this say? For a particular reaction is K and A. Let's see. Let's be complete. A to what power? First power. B to the second order. Okay. If the initial concentration of B is increased from 0.1 molar and increased to 0.4 molar, the initial rate will increase by which of the following factors? Well, how much are we increasing? What's the ratio of this one to that one? 4 times, right? We're increasing the concentration by a factor of 4. We increase the concentration by a factor of 4 is in here, and then we square it. So we're actually increasing the rate by 16, factor of 16, right here. Oh, notice I didn't have time to clean up the. It picked up this one, A, B, C, F, F, G for J. So I was in a hurry. So what if we did the same thing for A? Right. Went from 0.1 to 0.4. What would that do to the rate? Let's do that. Okay, we've gone, let's say both of them from 0.1 up to 0.4 and 0.4. Okay, so this is a 4 times increase and this is a 4 times increase in these concentrations, initial concentrations. So this has the effect of 16 times. What does this one have? It's just 4 times because it's only the power of 1. What's the overall increase though? $64 times. Because you've increased it. This factor did it by 16, this one did it by 4. So the overall is going to be increased by 64 times. That's 9. Should be able to get the next one. Yeah, 10. 10. For which order reaction is the half-life of the reaction proportional to 1 over K? Half-life. Proportional to, that's what that means. Proportional to 1 over K. Which ones are proportional to 1 over K? Well, let's see. I don't trust my memory. So look at useful information. And it should have a half-life state. Yeah. It doesn't tell you which one's which, but well, sort of it does, because it gives you the integrated rate laws. If you look at that right-hand column, integrated rate laws, and then below them the half-life. So the half-life for a 0 order is what? Right. Is it it's A0 over 2K. Okay, how about first order? T1 half equals what? 0.693, I remember that one. And that's over K, right? Just one K. Yeah. And the last one, second order, is half-life equals 1 over K times A. There we go. Okay, so now we got our half-life expressions for each of these orders. So which ones are proportional to 1 over K? All three of them. Okay, so that makes this one all of the above. They're all proportional to 1 over K. Roll this one. Let's see. Yeah, let's roll. There we go. 13. Of the following choices, which type of collision is most likely to be the rate determining step in a proposed mechanism? Okay. First of all, which step in a mechanism controls the rate? Silence. The slowest one controls the rate. So out of these different types of elementary steps, which one would be the slowest? The term molecular. Why? Because you have 3 reactants that have to come together with the right amount of energy and the correct orientation. You know what the probability of that happening? Very, very low. So based on probability alone, we can say this is going to be the slowest step. If any combination of these is part of a mechanism. Right? So that one right there is going to be the slowest. I don't even know what they mean by non-molecular. I think it was just a filler. How about 14? Let's see here. Okay, we're decomposing hydrogen peroxide. And we're giving it following. I better write the overall reaction here too. 2 waters, yeah, 2 waters plus an oxygen. And then the following mechanism says step 1. I should have given that step, told you which step is which. Is we're going to take one of these, right, and it's going to combine with iodine. There's no iodine up there. Something rotten in the state of Denmark. Okay, and then we're going to take another one in the second step and combine it with this intermediate. So that was nowhere up here. So then what happens? Now we produce another water. That's good. There's a water, 2 over here. 2 of these over here, 2 of these over here. That's good. Where's the oxygen? Oh, here it is. Oh, and we get our iodine back. Okay. What's the catalyst in this reaction? Is there a catalyst? Yeah. Iodine goes in this end, comes out the other end. It's not an intermediate because an intermediate is created by one of the steps. So that's an intermediate. And it's reconsumed over here. It's consumed and used up. So if we add this together, we should get that equation. Because this cancels that, But this goes in on the front end, comes out the back end. That's a catalyst. Now, theoretically, you can have, say, 4 steps, and the catalyst could come in this end and go out in one of the other steps before you get to the end. As long as it's part of the reaction, the slowest step, then it will have an impact on the overall. If it's part of one of the faster steps, then it won't have any influence at all, because the rate's determined by the slower step. So if it's got to be the slowest step here in order for that to be the catalyst. See what I mean? Let's see here. Yeah, about 15. Okay, we're gonna need that. We need that data above. There we go. 17. I have a feeling I'm going to need some space for this one. What's the order of the rate law with respect to MnO4? All right, so here we have 4 experiments. 1, 2, 3, 4. Independent experiments give us different rates, and they're different. Some are different concentrations, they vary. But we have some of these experiments, we have matching rates here and here, matching concentrations here and here. But we allow manganese, the manganate ion, to vary here. So that's the one we focus on, right? We're trying to get at the order for manganese. So we want to ratio this one and this one, the rate laws for this one and this one, so that we can be left only with that term, and then we can deduce the order for it. Okay, is that fair? We're on the right track. Okay, so since it asks only for the order of MnO4, we don't have to mess with the rest of it. It just asks for the order of that term. So we write the rate law, which would be the reactants only. So the rate is equal to K times MnO4 minus to some power. And then we have the next term, which is H2. We did this one in class, didn't we? And then hydrogen. And this is M, and we made that P. Right there. Okay, so that's the overall rate law. Now, if we notice that when we change the rate, the concentration of manganate from 1 to 2, we got an increase in rate. So if we're going to ratio them, it'd probably be more efficient to ratio the second one to the first one. That'll give you a positive of a non-fraction, a whole number for the ratio. So we're going to say the second reaction will give us this. Rate is 8 times 10 to the minus 4, right? And that's equal to K times MnO4 minus to the N. Oh, we need values. I'm sorry, the values in here. 2 times 10 to the minus 3. 2 times 10 to the minus 3. There we go. And then we have this one to the M power. And need a value there too. That's 1 times 10 to the minus 3. And then hydrogen ions is 1. And this is to the P. And then we're going to ratio that second one to the first one. And this is a 4, correct? No, it's 2. 2 times 10 to the minus 4. And that's K. And this value now changes to 10 to the minus 3. And this one's still 10 to the minus 3, 1 times 10 to the minus 3. And this one's still 1. Okay. So what do we get when we ratio those two? Okay. 2 into 8 is 4, right? But they're the same power. Okay, so the ratio of the two is 4. All right, how do I know that? Because 4 times 2 times 10 to the minus 4 is 8 times 10 to the minus 4. Just checking myself. Okay, K's cancel. These terms cancel because they're both the same. And the ratio here now is 2 times 10 to the minus 3 to the n divided by 1 times 10 to the minus 3. Yeah. Okay. So remember the mathematical rule. If these terms are to the same power, then we can bring them inside like this. And they're all to that power. Okay. So that means that 4 equals 2 to the n power. Okay. Everybody follow me on that jump? Okay. That's 2 divided by 1 is 2 to that power n. So n, excuse me, not that one. N has to be equal to 2. 2 squared is 4. And so the answer to this question is C. The order of the rate law with respect to MnO4 is 2. Okay, that's one way. That's the method of initial rates to answer Emma's earlier question. That's one of the ways. And if it asks for any of the others, you just set up the ratio, write the rate law, and set up the ratio for whichever one, allows the term you want to change and keep the others constant. That way, when you ratio them, they'll cancel. That's the trick. Okay. Roll time. Okay, that potential energy diagram is for the next question. So let me go down like this so we don't confuse it. 18. The rate law for the reaction 2NO plus O2 yields 2NO2 is this. Okay, and then we have NO to what power? 2, and O2 to the first power. So there's the rate law for that reaction. Oh, this is kind of like the earlier one we did, right? Repetitive. What happens to the rate when the concentration of O2 triples? So if this one triples, what happens to the rate? It's to the first power, so it triples. Okay, the rate triples. Let a duplicate slip through. Okay. How about, oh, there's one. What happens if I do this? Yeah, I figured. Knock it off. Okay, just checking myself. Yeah, we can do both of these. I put these two on the screen. The first one is independent, and 24 is independent. 25 relies on that previous statement. So 24. What fraction of a reactant remains after 5 half-lives of a first order reaction? Okay, what's the half-life for a first order reaction? 0.693 divided by K, right? I think that's right. So that's the first order reaction. All right, so we're going through what? 5 half-lives. We're going 5 half-lives. What fraction of a reaction? You know what? We don't even need to know that. Because the definition of a half-life is after a certain amount of time, half of it remains. It doesn't matter what reaction it is. It works for any of them. So after a certain amount of time, half of it's there. If we go another half-life, how much is left? Well, actually, maybe we do need to know that this is a first order, because now the initial concentration has no impact on the half-life. Right? It doesn't change with concentration. Yeah, that's important. Okay. So after 5 half-lives, what do you got? Well, after 1 half-life, what do you got left? Well, you got half, right? So that's 1 half-life. How about 2 half-lives? You got half of this left, right? So that's a quarter of the original. Okay. After 3 half-lives, what do you got? Right. Half of a half of a half. After 4 half-lives, what do you got? 16. And after 5, what do you got? 32. So 1/32 is what you have left after 5 half-lives. The other way to do that is, mathematically speaking, your math teacher will probably do it this way. 2 to the 5 power. 2 times 2 times 2 times 2 times 2. 2 to the 5th power. And that should be 1/32. But I thought this explanation would be easier to grasp. Okay, for 25, we need that information that's given above. The following reaction refers to this equation. So we have 2 A2s plus B. These are diatomic, right? And yields 2 Cs. Okay, this is a proposed mechanism. So step 1 is fast. Like A square plus B square, A sub 2 plus B sub 2 yields some intermediate plus C. And then step 2 is the slow one. In fact, very slow. So now we take another A2 plus that intermediate and yields C. Right? So which step is the rate determinant? Oh, this wasn't all that bad after all, was it? Which one is the rate determining step? Well, of course, it's that one right there. Step 2. Could you propose a rate law for this if you were given these things? We did one of those in class, right? Nah, probably better not. It'll eat up too much time, and I got to get through some others. Maybe one of the others has that approach. I can't remember. Let's see. Okay, 26 stands alone. That stuff below it is something else. So 26. In fact, that looks like the one we were just on. I bet this one approaches the question that I was asking earlier. For this reaction, where we have coefficient of little a times A yields products. Okay. The initial concentration of A, we're saying, is 6.4 molar. And the first 2 half-lives are 60 and 30 minutes. Okay, so let's do it this way. Let's do concentration of A in this one and time in this one. So at time 0, it's 6.4 molar. After the first 2 half-lives, first 2 half-lives are 60 and 30 minutes respectively. So after 60 minutes, that's the first half-life. So we'll have half concentration there, right? Okay. Second half-life is 30 minutes. So it goes 30 minutes. We may not need this information, but that would be 30 plus 60 is 90. So for the whole reaction after 90 minutes, you have half of that again. What's that? 1 point. Six? Yeah, 1.6. Okay, if this reaction is known to be zero order, calculate K. Oh, okay. So we're given zero order. So that means the rate law, we may not need this either. The rate law is K. Actually, it's K. It's zero order. So, and the half-life equation is 2 times the initial, I believe, divided by K. Is that right? That's why I put it in useful information. Nope. 2 times. There we go. All right. If we know it's, I mean, you're given it zero order, so we could use either one of these. We could say, okay, 6.4 is the 60 minutes is the half-life. And then the initial concentration is 6.4 to K. So we just solve for K. Right? So I'm swap places with K and 60. So I have 6.4 over 2 times 60. Correct? Yeah. So let's see, 6.4 divided by 120. .533. But that was 0. 0, 5, 3 is the K. So, oh, it's in scientific notation. 1, 2. 5.33 times 10 to the minus 2. I guess that would be this one. Okay. And technically speaking, it should only be 5.3, right? Because it's multiply divide rules and significant figures. And you've only got 2 here and you've only got 2 there. Well, you've only got 1 there actually. So best answer of all of those, I guess you could technically say none of these because that's got too many significant figures in it. But I'm going to run through them when I'm grading something like this. I'll grade C. And then if you think it should be none because of significant figures, you can make that argument and probably get credit for it. That's the difference between live testing like this and machine testing like standardized SATs and ACTs. You got no recourse there. Let's see. Let's skip one. 31. No, there it is. That's good. 31. The rate constant for a reaction at 2 different temperatures is given below. Okay. So when T, let's say T1 equals 30 degrees C. What are we talking about here? What's the activation energy? We're looking at Arrhenius. Remember the Arrhenius equation? It's in useful information. Let's see. There it is right there. It's on the right-hand column toward the bottom. So we know we're going to have K to do this calculation. That's 303 K. Might as well put it in there. And T2 is 49 plus 273 equals 112, 322. Okay. Now K at this temperature is 1.38 times 10 to the minus 4 reciprocal molars, reciprocal seconds. And one at this temperature is 1.21 times 10 to the minus 3. And K's gone up with an increase in temperature, which seems reasonable. Okay, so what's the equation we use? Well, let's see. K2 over K1, natural log of K2 over K1 equals E sub A over R. There's our unknown. And this is times 1 over, which one is first? T1 minus 1 over T2. There you go. So all we have to do is plug in the numbers. Right? We'll plug in the K2 right here, put this one down here, and put that one right here. So let's see. The second one comes first, 10 to the minus 3. I'm going to leave out the units. And the first one comes on the bottom, 10 to the minus 4. That's equal to E sub A over R. So what's R? The gas constant, right? So we look it up. It's in here somewhere. Here it is. We need the one with energy units. Yeah, 8.3145. There we go. And then this one is times 1 over T1. 303 minus 1 over T2. 322. There we go. So now all we have to do is solve for E sub A. Okay. You can do it in steps. Like we'll take the inverse of 303 and then the inverse of 322, subtract it. So this one, I need some more decimal places here. Hold on a second. Just plug it. And let's say 6. Back up. There we go. That's better. So this one is 1.947 times 10 to the minus 4. There. And then this one, you divide this one into this one, 1.21 to the minus 3, and then 1.38 to the minus 4. Divide that into. And this is natural log of 8.76816 equals that stuff. So let's go ahead and take the natural log of that while it's already here in my calculator. This one is 2.171. Okay. So this now is that whole term there times this term. So we divide this into that. Do you see that? That's the next term. Okay, so we're going to take, we flip this and divide this by that number, 8.3445. Okay, that's 2.34. 2.342 out of 10 to the minus 5 times E sub A. So all I need to do to get E sub A is to divide this one by that one, right? Yeah. And I get E sub A equals 9.27 times 10 to the 4th joules. So kilojoules. All right. So how do we do that? Kilojoules. A kilojoule is 10 to the 3rd. Right. So if we reduce this one take that one down to 10 to the first and bury that 10 to the third over here, that's 9.27 times 10 to the first kilojoules, or 92.7 kilojoules. And should be right here. Okay. I should have scrunched this up a little bit more so I give me more room in here. My course was already set. That was 31. Let's see, 32. All right. Consider the following balanced reaction and the experimental results that follow. Okay, so this is 2NO all time plus 2H2 yields N2 plus 2H2O. All right. So based on this concentration, right, I'm just going to write things underneath there. And the rate is over, move this up. Right. Right. Okay, so the rate for the observation experience following. Okay. Okay. So this is a initial rates problem. Right, we've got separate experiments. When the concentrations are this, get that rate, this, you get that rate, this, you get that rate. And we have 3 experiments because we only have 2 terms. Right? And 3 experiments will give us every combination. So if we have 0.15 molar, 0.02 molar, we get a reaction rate of 0.60 molar per minute. And then we have 0.15 here, but we let this one change 0.40, then we get a reaction rate of 1.20. And if we have let this one change, this one goes back to the original here, then we get this rate. Okay. All right, I probably should have scrunched those some more, but how do we get at the order for this one? Well, we need to let that one vary. It changes from here to here, and it stays the same from there to there. So we're going to ratio this one to that one. So the rate of this one is 2.40 equals what? Well, the concentration of NO here. Well, let me do it this way. Let's write the rate law first. That way it'd be less confusing and less likely to make mistakes. So we're going to have NO to the, let's see, let's make it N order, and then H2 to the N order. Now we can ratio. So we're going to ratio this one and that one first. 2.40 equals 0.30 to the N, and H2 is 0.02 to the N. Ratio that one to this one, 0.60, and then this one has changed to 0.15, and this one stays the same. Or did I leave out? Let's see what I left out. It looks fine to you? No. Every rate law has a constant. I planned it that way. Okay, so now this term cancels, right? This one cancels, and this ratio is what? 4 times? 4 times 0.6 is 2.4. So that's 4. And this is what? 0.5 into 3 is 2, right? to the n. So n equals 2. So this term right here now is 2. Okay? All right. So now we're going to do the same thing, only this time we're going to ratio and let the hydrogen term vary. So if we do that, we'll use either this one and this one, or this one and this one. Doesn't matter really. Let's use this one, and this one. So 2.40, I should have left that stuff up here. I'm thinking ahead. 020. And this one is 1.20. And now it's 0.04. Excuse me. No, looking at the wrong terms. Oh. I'm sorry. It does have to be these two. Right? Don't let me make all these kind of mistakes. This one has to stay the same. So let that one vary. So now we have to do 1.20 here, 0.60 here. And then 0.15 for both of these. Now we let this one go 0.04 because that one matches 1.2. And this one is 0.02 here. Okay, so these cancel again, those cancel. Now we have this one, which is 2, right? 0.6 into 1.2. And this one is also 2 to the m. So m has to equal 1, right? I guess it's all right. So that means this term now is first order. Okay, so the answers are given as n comma m, which would be this one right here. 2 and 1 are the rate law orders respectively for NO and H2. Okay. $32. Let's see. Scroll time. Yeah, we'll get both of those on there. Let's see. 33. The second order reaction. NO plus O3 yields NO2 plus O2. Okay, we got the rate constant at the temperature, and the activation energy has been measured to be. Does it matter that we know the second order reaction in this case? Right? Because if it's second order, that means it's first order in this one and first order in that one, or it's second order in that one and this one is 0. That's the only possibility. And it doesn't matter really, because we're after the activation energy. And is there order in the activation energy anywhere? No. The order is not anywhere found in the activation energy equation. So that's just blue smoke. It's trying to confuse you and say, oh, you got to fret about second order. Well, what was second order? Oh, you don't need it. Okay, so we're given let's see, rate constant has been measured. The K, let's say K1 is 1.08 times 10 to the 7th at a temperature 1 of 298 K. Okay. And the activation energy has been measured to be, okay, we're actually given this one at 11.4 kilojoules per mole. Okay. Over the temperature range 195 to 304. And so we're within the temperature range. And what is the rate constant at 233? So we've got T2 is 233. Oops, wrong K. A. And we want to know what this one is. Okay. Temperatures are right, they're in Ks. We've got this one is our rate constant K1. We want to know K2. And the units really don't matter because calculation is going to give us the same units we started with here. But our R value is what? R is 8 point, what? I got to look it up. 3145. 8.3145 joules per mole K. Notice that's in joules. The constant tells you that your activation energy has to be in joules units. So we've got to say this, 1.14 times 10 to the 4th joules before you put it in the equation. Otherwise, we get the wrong answer. Okay, so back to our Arrhenius equation. I'm not going to rely on their memory. I'm just going to read it right here. So natural log of K2 over K1 equals E sub A over R times 1 over T1 minus 1 over T2. All right. This K2 is our unknown right here. So we can plug in everything over here that we know at this point, right? We know that value, 1.14 times 10 to the 4th, and we know this value, 8.3145. And we also know these values, 1 over 298 minus 1 over 233. T1 minus T2. Did I write that correctly? Yes. Okay. Just checking. Right. This is nothing but math. We can reduce this to a single number. Right. So why don't we do that first? I'm going to take the reciprocal of this one and subtract the reciprocal of that one first. So 298, find my reciprocal key, there it is. And then 233, and reciprocal that, and then subtract. Okay, get a value, a negative value actually. And then I'm going to take this one divided by that one and multiply what I got over here. 1.14 exponent 4, actually I can multiply it now, and then divide by 8.3145. So over here, I get a negative 1.2835. And over here, the K2 is unknown, and the K1 is here. 1.08 times 10 to the 7th. Okay. Now, what do we do with an unknown inside a logarithm? You know how to split logarithms? I'm going to have to erase some of the stuff up here. So we've got that in our equation already, so I can do that. Okay, I will leave that there. All right, so we take this. The log of A divided by B is the same as the log of A minus the log of B. Say that again. The log of A divided by B is equal to the log of A minus the log of B. So we would say the natural log of K2 minus the natural log of 1.08 times 10 to the 7th. And that's equal to a negative 1.2835. Okay, so far so good. Now, we just need to take the log of this. Let me do that. 1.08 exponent 7 to take the natural log of it. Okay, so this is minus 1.6195 times 10 to the first power. Okay, that's that, that's that. So this would, on that side, would be a positive. Right? We just take that over there and add it to that value. Okay. Okay. It's in my calculator already. All I have to do is punch the add button. And on this side now, I get 1.491 times 10 to the first power is equal to the log of K2. Okay. So how do we get at K2? I'll just put it in here when I find it. We take the anti-log of this value, right? Definition of logarithms. Log base E, of course. K, K2 would be E to that power. That's what that means. Remember that from logarithms? This is the power of the base that equals that number. That's what logarithms mean. So in your calculator, how would you do that? Well, you got this number in there already. All you need to do is find your e to the x, which is function above the ln in mind. It'll say e to the x. You just say function e to the x. That means k, well, I'll just write it down here. K2 now is 2.99 times 10 to the 6th. All right, which one's closest? This one right here. Pick your best answer. Okay. In a problem like this, students usually get lost in the math. You'd be very methodical about it. Remember your rules. Okay. From, I don't know, where they teach this, math or algebra? Algebra. Algebra, okay. Yeah, remember your logarithm rules. That's important for this operation. So we did two of them here, right? We split this one by one rule, and then we did this one by another rule. The anti-log, or the anti-ln. That's what it would be called. All right. Let's see. Oh, 34. Doing on time. Okay. We got till 10 something for the lecture. 10:25. I'd like to finish early so we can talk about the lab a little bit before we get in there. Let's see. The first order decomposition of H2O2 at minus 28. Okay. H2O2 decomposition. We know what that is. We probably don't need to deal with it because we're talking, this is the reactant. But the temperature may be important, minus 28 degrees C. Occurs with a half-life of 50 seconds. Okay. So this half-life, T1/2 equals 50 seconds. Starting with a concentration of 25.2. So the concentration, initially concentration, is 25.2 molar. What will be the residual concentration of H2O2 after 5 minutes? Okay, this is important, first order. So this is, we write the rate. it would be K times H2O2 like that. So what's the, but that doesn't help us any because it doesn't have a time variable in there. We have to use the integrated rate law for this one. So the integrated rate law for the first order is the natural logarithm one minus KT. So this is the natural log of H2O2 equals minus KT, is it plus? Yeah, plus log. Negative KT plus the natural log of the initial concentration. Initial concentration. There we go. All right. So in order to use this, we've got to figure out what the K is from the half-life. So this half-life for that one is, I remember this one, 0.693 over K, correct? Yeah. So this will allow us to calculate K. We can put K in here. Okay. So what's K? K equals 0.693 divided by 50. Right, so let's do that. 0.693 divided by 50. 1.386. 1.386 times 10 to the minus 2. Yep. Okay. Now we can put the K in here, in that value. We can put the initial concentration in here. And then we have to put in a time value. What's the time value? 5 minutes. But this is in seconds, so we got to convert it. T then would be equal to 5 minutes times 60 seconds per minute, be 300 seconds. Okay. Good so far? All right, so now we can say natural log, this is our unknown. We want to know what that concentration is, minus K, which is 1.386 times 10 to the minus 2, T, which is 300 seconds, plus natural log of our starting concentration, which was 25.2 molar. Okay, now we check to see, do we have one unknown? Yep, there it is right there. So let's do all of this stuff. Take the natural log of 25.2, I'd do that first. Log, and this one is 3.2268. And then multiply these two together. So I'd say 1.386 exponent minus 2. And then 300 times that. I forgot to change the sign. So I change the sign. There we go. Now I can add this one to that one. And that gives me minus 9.3116 times 10 to the minus 1. And that's equal to the natural log of H2O2. Okay. Okay so far? Or are you too busy copying? Okay, I'll take a breather just a second. All right. So here we are again with e to that power is this value. And so I got that one in my calculator. I just say e to the x. And let's see. This, oops, I do it. H2O2 concentration after 5 minutes will be 0.394 molar. right there. Okay. Sometimes when negative numbers show up in these types of operations, it freaks out a student. But don't worry, when logs are involved, I don't give negative numbers a second thought. Okay? They'll all come out in the wash. If you did everything else right, of course. Now it's 34. All right. Let's see. Ooh. Okay. The next two questions, 39 and 40 and 41, are based upon this structure. Okay, that's kind of hard. I can't get them all on the same page unless I shrink it. What if I shrink it? That might be too small. Let's look at this diagram first before we start answering questions. In fact, and just draw it with a different marker. So that's green. What about blue? So we have this diagram, right? And this is reaction progress. And this is energy, actually potential energy of the components. And we got this possibility. We're going to go up like this, like that. They go back down like this over here. Reactants, products. And then we're going to have another one that goes like this. So let me make this one dotted. Looks like this, back down like that. Okay. So the difference between here and here is A. Okay. The difference between let's see, I don't want to put it over there. I know it's right on here. Well, I guess I could. We go from here all the way down to here. This is B. And then if we go from here to here, right? This is C. And if we go from here to here, this is E. And then this is F. There. Oh, D, forgot D. D is from here to here. Okay. So now we got the diagram up there. I can scroll and we can read the questions. Let's see. Yeah, we can get them all on there. 39. So 39 wants to know which letter shows the activation energy without the use of a catalyst. Whoa. Oh, yeah, it's up there. Just checking. Which one is without the use of a catalyst? Well, we start here with our reactants, correct? How much energy does it take to get to which one? The one without the catalyst is the bigger one. It takes more energy. So it's E here. That distance is activation energy without the catalyst. Which letter shows the activation with a catalyst? Well, it starts at the same place, but it only has to go up to here. This is the lower energy trace. So that one's A. I forgot to write my arrows. Okay. A. 41. Which letter shows activation energy for the reverse reaction without a catalyst? So now you're starting from over here, reactants. And you have to go from here all the way up to there to activate that reaction. That's C. Correct? Okay. It's not one of the questions, but which one of these is the enthalpy of the reaction? Delta H for the reaction is equal to what? That one right there. It's F. This is where they started. This is where they ended. That's the enthalpy for the reaction. Is this a endothermic or ectothermic reaction? Final minus initial. Final has a lower value than the initial, so this one minus that one. This one's bigger, so it'll be a negative. That makes it exothermic. And you can reason it this way. Starts off here. You can't create or destroy energy, so the energy it had here, it's got to be there when you get over here. But this is only the energy in the molecules. So where'd the rest of it go? Out of the system, exothermic. Okay, that was 39, 40, and 41 based on that diagram. I think the next one is also a diagram. Yeah. Let me scroll up a little bit. We got two questions for that one. Using this graph. All right. This is concentration versus time. Concentration versus time. And notice that it's not just concentration. Actually, that's not right. That should be natural log of concentration versus time. Shouldn't it? Let's look at this. Natural log. So if you have a natural log of the concentration versus time, what order reaction is this? It's either 0, 1, or 2, right? So 0 is raw data. Right? First order is natural log. Second order is inverse. So this is a first order reaction. This is first order. All right? That's important because the equation of this line should look like natural log of the concentration of SO2 CL2, SO2 CL2 is equal to negative K T plus natural log of SO. Yeah, that's an O. It's an oxygen. SO2 CL2 initial. Right. So this format is a straight line with a negative slope. Okay, yeah, we got a negative slope. That checks. Okay. We're given the line equation right over there. Right. So there's Y. And this slope value, the K, is minus 2.20 times 10 to the minus 5 T for X. So let me just say this, natural log of this one, SO2 CL2. And then this one is a negative 8.87 times 10 to the minus 5. That's this term right here. It's a negative. So the y-intercept is going to be a negative value, right? And it's right up there. It looks like it's on the 0, but it's just under the 0, right? Very, very slightly under the 0, negative territory. And the slope is negative 2.2 times 10 to the minus 5. So the slope of this line is that value times T. Okay, now let's answer the questions. All right, 42. What order is this reaction with respect to? Okay, we already answered that one, right? First order, which would be B. B. First order. 43. What's the value of the rate constant K? Well, negative K is this value. So K is equal to 2.20 times 10 to the minus 5. Right there. Okay? That's how you read that graph. That's the whole point of those questions, is can you read the graph and get information from it. All righty. Let's see. Oh, we're done.